Hi, everybody. I'm Aishwarya. Thanks for the introduction, Francesco. So today we'll be talking about vision and language models. Since many of you are probably joining the field quite recently, I'm guessing you've seen all of the material out there on like Gemini, Llama, GPT-4, but maybe less about how we got here, and also like why we do things the way we do right now. And so that's basically what I'm going to be starting with. This is the roadmap for today. We'll start with exactly what are vision and language models, and then we'll talk about popular multimodal tasks, what they were in the past, what they are now, and then we'll look at how the models have evolved over time, the architectures, the pre-training data sets, and like how multimodal fusion works. And then we'll finally look at how the field shifted to the modern VLMs of today, which are based on large language models, as I'm sure you have heard of. And then I'll show you a cool demo from this project that I work on, which is Gemma. Cool. So starting with introduction, what are vision and language models? So AI systems that jointly process visual data, like images and video, and language data, text, to understand, reason, and generate multimodal outputs. And so this can be vision to language, like captioning, question answering, grounding, detection, etc., or language to vision, which is like image and video generation from text prompts. So just to give you a disclaimer about what this talk is going to be about, it's just going to be about the understanding part, which is vision to language. And I think there's a talk on Friday by Sander on diffusion models, so that will be the other direction. Cool. So let's start with some examples of classic vision and language tasks. This field pretty much started with image captioning as the main task, and the most popular benchmark for this was image captioning on Coco. So that's the top left one you can see. There's, kind of a varied range of diverse scenes, mostly like things captured by actual people. So there's a lot of stuff at home. There's a lot of like people playing Wii because it's kind of old now. And yeah, so the task is to give a natural language description of the image. Then the one below that is image text retrieval. So what that is there's like a large data set of images and text. And for a given image, you need to rank all the text according to how similar they are. So that basically, this is what you would use, for example, if you were going through your photo library and saying like, okay, it's a picture of my cat. It's going to use this. Okay, it's going to use this and embed that textual prompt and then find using similarity metrics through all the images in your library. Don't know what's up. Okay, let's hope it stays. That's fine. So that's image text retrieval. And both of these tasks are coarse grain tasks. Not sure why it's doing that. Should I just unplug and put it back or something? I mean, it has a... Okay, it works through the...
All right, sorry for the interruption.
No worries. So I was saying that these two tasks that I just described, they're pretty coarse grain. So like what I mean by that is it's a high level understanding of the image, whereas the ones on the right, they're more like fine grained in the sense that you need to know about parts of the image, more like specific pixel level information. So tasks like referring expression, segmentation, and detection, where you get some text as input. So here, for example, like wipers on a train, and you need to predict the segmentation mask of the object which is being referred. So these are more like they are harder tasks, but compared to like what we will see next, it's still quite simple. Basically because these tasks didn't cover most things which humans actually do, like reading documents, interpreting charts, reasoning over math problems, they were still kind of limited. And so this gap kind of inspired the new generation of benchmarks that we'll see next. So now we have more reasoning intensive benchmarks that go beyond natural images and into domains like scientific diagrams from research papers, documents, and like college level reasoning problems, for example. I've just listed some of the ones that are commonly used to track progress of late. And the common thread between them is that they all require much superior understanding of language in conjunction with visual understanding. In the past, the language bit wasn't so intense, like it was quite simple, like wipers on a train, you're not like saying very complicated things. And the reason these new tasks are now possible is because we have large language models which are trained on like basically the whole internet, and that makes them much more powerful in understanding like the prompts. Okay, so now that we know the type of tasks that we're trying to solve, now we can look at how the modeling paradigms changed over the last like 8 to 10 years in response to the different tasks that people are interested in solving. So I've tried to illustrate like the typical canonicalization of vision and language understanding system. It's illustrated with an example of visual question answering. So there's an image, question, and then the response you want is the answer. So overall, the important components are a visual feature extractor, a text feature extractor, a module that somehow fuses the information between these two modalities, and gives you the final input, final output using like a prediction head. So we'll see how each of these components have been instantiated over the last 10 years through the vision and language progress, and also how they were trained. So the very early attempts at vision and language models were, as I mentioned, like image captioning systems. And so the images were passed first to a CNN that was pre-trained on a large data set, which is usually ImageNet. And the last layer features were either fed to the first step of the RNN or at every step, depending, like there's many different ways to do that. And then the RNN predicted the caption autoregressively based on the information contained in the image. The main problem here was that all of the information had to be compressed into a single vector, because at that time we had, like before 2014, it was encoder-decoder models, which were very popular. So the encoder in this case would be the CNN. It would give you this one like compressed representation, and then the output would be given by autoregressively by a different RNN. In 2014, there was this really game-changing paper called Neural Machine Translation by Jointly Learning to Align and Translate. It was for machine translation, so just language-to-language text-only task. But the same idea was used basically to, so here is an example of like how it would look for a particular word attending to all over the input sequence instead of just having access to one compressed representation. So you can think of it as like you have the whole image. Now it doesn't have to only look at like the final one embedding of it. It can look at the entire grid features. So this is what, this is what it looks like. The multimodal block now is attention. So the RNN can look at the output of the CNN of the whole image. And so basically, this is the first kind of paper which used the idea of attention for image captioning. It was called Neural Image Caption Generation with Visual Attention. And a cool like bonus point you get from this kind of approach is that you can also get a bit of like interpretability, because you can overlay the attention mask on the image and see what the image's model is kind of looking at while it's saying a particular word. So this was the very beginning. And then the next paradigm shift was, instead of having attention over the full grid features of the image, a couple of papers introduced first extracting salient objects using a faster RCNN object detection system, and then attending only to these objects. And so this has pros as well as cons, as you can imagine, because on the positive side, this meant that instead of wasting computation attending to the whole grid, you can actually just focus on the parts that are probably going to be important in the image. It was introduced actually for the task of image captioning, and also was used in the VQA challenge in 2017, and it won the challenge that year. So, but on the negative side, an important point to note here is that because it uses this object detection system, you can't really fine-tune the features end-to-end anymore, as you could do with the CNN-based system, because FastRCNN has many non-differentiable components. And so basically you need to know in advance what concepts you could be interested in. So for example, in this image, if you are trying to solve VQA and you're like, what is the color of this man's shoes? Then your object detection system has to be pre-trained on a data set which has shoes and the colors in its label set so that it's able to answer this question. So that was kind of a blocker at that time, because the main object detection data set, which was cleanly labeled, was again MS Coco from Microsoft, which had only 80 classes. And as you can imagine, people want to ask questions in the wild about a lot more than just 80 things. And so to cover a larger vocabulary of object classes and attributes, this paper called Bottom-Up, Top-Down Detectors, they train on the visual genome dataset, which also came out around the same time in 2017, which had 1,600 classes. So a lot more diversity in concepts, and also a lot of these were annotated with up to 400 attributes, which meant that you could answer a wider range of questions. So now you understand why this object detection system was actually quite kind of important at this time in advancing the field. But sadly, this is not really scalable because object annotations are kind of hard to come by. It's quite expensive to get humans to annotate bounding boxes. And of course, people tried pseudo-labeling using existing detectors to annotate more data, but it only goes so far. And so the progress on this front sort of stalled after a point. But I just want to recap with the same diagram. So far, we see that the visual feature extraction block was first a CNN. It was then replaced by this faster RCNN object detection system. And then the bottom-up, top-down version of it basically became the de facto image feature extractor for 4 or 5 years. From 2017 to 2022, everybody was using this in all kinds of modules. So yeah, it's a cool paper to read if you're interested. And then, of course, there was this game changer, which was CLIP. It showed that training on large web-scale image text data enables learning visual representations that transfer much better to all kinds of tasks like captioning, VQA, etc. So now you don't need to worry about how do you learn about all of these new concepts that people could be asking questions about. It exists on the internet. And so image text contrastive loss that CLIP basically used was used to basically push together representations that are about the same concept. And if you have an image and text that are not aligned, you push their representations away. Of course, contrastive loss has been around for a while, and it's been used in self-supervised learning a lot, but this was pretty much the first time it was shown to be so effective in learning from language supervision. So that's why this was pretty cool. And then just want to point out that similar ideas were also used for learning object-based representations. So if you were still interested in kind of leveraging the fact that you want your model to learn object-centric representations, there are some reasons for doing that. Then you can also use this contrastive loss, but between phrases in the image. So suppose there's a man and a woman cutting a cake at their wedding. So you have a bunch of nouns, which are man, woman, cake. And so basically you would have the text representation of each of these phrases, and then the visual representation of each of these objects, and you would try to bring them close together, and for unrelated things, you would push them apart. And that's the idea behind MDTer and GLIP. Okay, so at this time, all the fields were going through the transformation. The ML community all converged on the same architecture. I'm sure you heard from Skanda today and from outside. Yeah, so transformers everywhere. This simplified a lot of things. Already the NLP community was pre-training on large-scale text data. BERT basically happened around this time. And so the vision and language community also jumped on this train, and they were okay, so now let's use this transformer on top of the bottom-up, top-down features. So at this point, they were still kind of stuck to the object detection framework, And so they would put a transformer on top, of the, sorry, on top of the object features. And like, oh no. No, it's okay. No, it's fine. I think it's okay. It's probably better just by directly. Yeah, so just the same diagram again. There's transformer pretty much everywhere, but there was still like this one issue with like still having some amount of CNNs in the picture. But at this point, the vision and language community was like, okay, we're still going to use this, pass the CNN, like the object representation features into the, you can see on the top left side, basically you put this into the transformer, and then the text is, just the embeddings. The problem here is that, like I said, it's not end-to-end fine-tunable, so the objects are kind of like their own thing, they're extracted on a different data set, and they don't really learn end-to-end. And the label set is also just within whatever the object detection annotations were, not actually what's on the internet. And so, yeah, this is a representation of like how that was overcome. Still have a CNN backbone, but like the transformer basically is trained end-to-end so that the queries can actually specialize based on the data sets that you are training on. Okay, and simultaneously, this paper from Lucas Bayer, Alex and all from Google Brain, they had this kind of realization that a lot of people wanted to train with transformers and were trying to do attention at the pixel level. When that didn't work, they were like, okay, let's use this kind of detectors. And it's kind of wasteful. Show the adapter. So basically what they proposed, which was like really cool, is that they suggested that each image can be tokenized as 16 by 16 size patches, which then are basically tokens, which can go into your transformer just like text tokens. And this was like kind of an important step because it enabled all of the, like both the modalities to be using exactly the same architecture. Okay, so now the question is, how do you fuse the two modalities? Because we've so far been talking about how do you learn the visual representation, and the text is already transformers, and like we need to talk about how to combine the two. So there's about 3 options here. So the first is late fusion. So when I say late fusion, the idea here is to have independent encoders. So at this point, it's already transformers. So like there's an image transformer, and then there's a text transformer. And at the end of it, you try to compare the outputs and learn a representation that brings together things that are similar. And so the pros for this are it's simple, it's scalable, like in terms of learning representations, you can train on very large data sets very fast. It's also very great for retrieval and zero shot. But the cons are that you have pretty much just coarse alignment. You don't have very fine-grained understanding of what's happening either in the text or in the image. And the reasoning is also kind of limited because it's, again, at a pretty high level. So just to visualize what this looks like, so I try to illustrate it here. The query key values from the image and the language, they pretty much don't interact at all. They only interact at the end through this prediction head, which, for example, in clip is like, you do a similarity through a dot product, and that's basically all you have. But of course, like what kind of fusion you use is very task dependent. It's not like a one size kind of fits all situation because not this adapter either, I don't know. Maybe it's my laptop. Is it overheating? I don't know.
What happened?
I didn't do anything. Oh, that was here.
Ah, that was here. Okay. I was thinking maybe it's like, yeah.
It's fine. It's fine. 1 second. Take a 1 second break. Okay. You want to do something?
So it wouldn't be a conference if there wasn't audio-video issues.
We try another one?
Yeah, let's try.
No, it's weird.
Ignore the glitches, they come back eventually. Yes, there you go.
Thank you. I'm A/B testing all of the doctors. Thank you. Okay. So as I was saying, maybe you at this point think like, oh, like the fusion is so late. This is kind of useless. But wait, no. Late fusion is really fast and efficient. So separate feature extraction pipelines for image and text means you can basically independently do the computation, store it, and then it enables really quick retrieval, especially when you have extremely large data sets. Again, with the example with your photo library, for example, you don't want to feed every single image with every single text together. You want to encode them separately, save them, and then quickly do retrieval. So in these kind of settings, late fusion modules are very useful. The next type is intermediate fusion. So somewhere in the middle is having separate encoders for image and text, but then you have some amount of cross-attention, self-attention, or some fusion modules to put them together. The pros of this approach are it's sort of a balance between modality-specific and joint reasoning. You can also use disjoint sets of data for training the encoders versus the joint training. This is sometimes useful, it can because the amount of noise that is tolerated during the vision or text encoder pre-training versus joint pre-training sometimes can vary a lot. So typically people use web scale data, which doesn't go through too much filtering for training vision encoders. But then if you still try to use this dirty alt text for training your language model, you will suffer. And so this kind of helps sometimes when you do disjoint training. You first have very good features for your vision encoder, and then you train on different data set when you're training together. And then the cons are that if the encoding is lossy, then there's no way to kind of come back from it. If you need access to ground truth, pixel level information, for example, if you're doing depth prediction, segmentation, etc., sometimes it can be worse to have a separate encoder versus directly giving it the image. And then encoders train on different data distributions. So this is also a negative because, for example, if your goal is to train the end system on medical sort of things, which I think a lot of you are, and your vision encoder wasn't pre-trained on it, then you're going to have problems unless you have enough pair data later. It's easier to find large scale unimodal data than pair data. So that's also another reason to do it. And visualization-wise, this is kind of what it looks like in the self-attention setting. So it's suitable for very intricate tasks where deep interaction between the modalities is useful, I don't know, reasoning tasks, VQA, things like that. However, it is slower and resource-intensive. Joint encoding of image and text demands significant computational resources. And also, like I said, if your data is noisy, you will see that it affects the training a lot more in this case. Okay, and then the last one, which is early fusion. So when I say early fusion, I mean really early, there's nothing after the image, because sometimes there's a bit of controversy around what is really early fusion. But in this case, I mean feed in image patches, feed in text tokens, and then just have the transformer completely learn everything from scratch. The pros are obviously very tight coupling from the start, rich cross-modal interactions, better suited for dense prediction tasks tasks like object detection, segmentation definitely would benefit from this. I think it's my computer. It's fine. I'll survive. It's okay. It's okay. Okay, cons. Yeah, so the cons are really high computational cost. Typically, you need to train for much longer if you're trying to learn these representations from scratch directly from the image, as opposed to having some pre-training already for the vision encoder. And also, it's really hard to scale to long text and high-res images, because let's think about it. It's the transformer, which is going to take all of these patches as input and then the text. And if you're giving directly the patches, you're going to have extremely long sequences, which makes it very computationally expensive. So yeah, these are some examples. You can look at them later. As far as I know, there's nothing really open source out there. But yeah, there's a bunch of like papers. And that's what it would look like. You just pass in the image and the text directly to the encoder. Yeah, that's cool. There's also hybrid approaches. Sometimes you don't want to like commit to one or the other. So retrieval using a dual encoder, and then you follow up with joint encoder re-ranking. This is actually a very cool idea. Sorry, I didn't put like a link there. I will add one later. But basically, you do the dual, like two separate encoders for very quick computation, and you get the options, like top n options for what is the most relevant images or text, depending on what direction you're going, and then you feed those jointly into the like full attention, so that you get like more fine-grained understanding. And then the third option is like using a joint encoder, but only with the first few layers fused. This is actually also gives very good performance. There's a paper fiber which does that. I'm waiting for the guy to finish taking a picture. Did you manage? No? I'll send you the slides, it's fine. Okay, and then let's talk about like how do you train these things? Again. So how do we train these things? There's different ways to leverage this large-scale data to learn representations, as well as learning the alignment. So the first is generative, which is captioning. So what is the loss here? It's next token prediction, cross-entropy loss. The pros are, of course, like the ordering and noun attribute alignment between like if you say a black shirt with white like collar and green buttons. It's a weird shirt. But yeah, so if you say that and then you look it up, it's like if you use that with the generative, with the captioning loss, it's your model that you train with it is more likely to actually be sensitive to like what is black, what is white, and what is green, whereas opposed to if you used a contrastive loss, which we'll see next, which treats it more like as a bag of words. The cons are, of course, like it's expensive, more expensive train. And you have like more expensive decoding. It takes also longer to train, and the alignment is only implicit. So examples of this kind are blip and lava. And then in the next, like lip style, of course, it's contrastive, and the pros here are it scales to noisy web data. It has strong zero-shot retrieval and classification performance, but the cons are that while training, you need much larger batch sizes to learn what you're trying to learn from this loss, and then the alignment is only coarse. So like I said, like it won't really be paying attention to which nouns are having what attributes. Examples are clip, align, basic. And then the last is like a loss which a lot of the models in between 2017 and 2021 used, which is like a binary classification on is this pair aligned. So you have like, the image, you have the text, it has very like dense like cross attention or self attention over this like pair, and then you have to like predict if it's aligned or not. It gives you much more finer grained grounding because it has full attention over the way it was used was attention over the entire sequence, and then you decide if all of the like respective noun attribute pairs are like maintained. The cons are it's hard to scale because negative mining for this kind of very fine grained like pairs is quite hard, and the loss itself is like a bit less generalizable because, for example, in the contrastive setting, it can be used directly for similarity-based like retrieval. Here, like it's unclear how you would actually use it, like zero shot after. Examples here are Uniter, Oscar, and Wilbert, which were all like models in that time. Okay, I think I should pause to like take some questions.
It's on. Can you hear me? Oh, cool. I just wanted to ask about the encoding part because in these images, it looked like you are encoding the Hello. Sorry, it's like I'm hidden here. I just want, like one of the images you showed, like the encoding part, it looks like you actually feeding in the query, the value and the keys from the attention layers. Is that what we are doing, or are we just feeding in the latent embedding vectors,
So it's
let's
fed
say?
as input. The whole thing is fed as input to the transformer. I was just trying to show that when there's cross attention, for example, the queries will be from one modality and like the keys and values will come from the other. And that's how you like do the cross attention. So yes, it's just through the keys and values in that case that the other modality is kind of accessed. Whereas in the full self attention, basically everything is just like concatenated and fed through. Then you have like attention over the whole thing and all of the blocks are reused.
Okay, thank you.
Yeah.
Yeah, so, hi. Sorry. Yeah, so my question is, when we talk about fusion strategies like adaptive fusion, so we generally use it in the late fusion strategies, but do we have any early or intermediate adaptive fusions that have worked well?
So like I said, fiber is an example. Basically, it's a model where there's two backbones, but then the backbones, like when I say backbone, by the way, it's like the feature extractor. That's like vision terminology. So basically, like the transformer which is extracting visual features, transformer which is extracting text features before you do like any sort of like further processing, those itself have some amount of cross attention. In fiber's case, it's a Swin transformer, and usually you would like take only the output, but in this paper, like some of the layers of the Swin transformer, the last few are basically already cross-attending to the text, so that the features are kind of sensitive to what the task is asking for, instead of just extracting it. You can think about it as the difference between like not knowing what you're going to need to look for in the image and just saying these are the features of the image, versus like already like being text aware, so that the features are modulated in a way that they're more useful. I have a full tech team.
Oh, sorry.
Sorry. Hey. I have another question.
Oh, that's not my computer.
So we're slowly replacing every single bit. Eventually, we'll change the projector.
Can I ask a question in the meantime?
Okay, let's thank the speaker again while she resumes the talk. It's a very stressful situation, but thank you so much.
Okay, hopefully people still remember what we were talking about. Three types of ways of training. There's different training losses. So we had captioning, there's contrastive, and then the matching. We went through that. Okay, oops, sorry. Yeah, so the chart on the left is basically from the CLIP paper, which showed that image text pre-training with contrastive loss is the most effective way to train, and they claim that basically you get an efficiency gain of like 3 times 4 if you go from just regular language modeling loss, which is the captioning loss. But then the image on the right is from the Kappa paper, where instead of just having an autoregressive prediction, they actually also have a parallel prediction loss. And so what that means is like given the image, you don't predict, like you don't have a causal mask. Sometimes you also have like to predict all the words at once. And this gives a much stronger training signal. And they show that basically training in this way gives you the same like scaling behavior as training with the contrastive loss. And why is this important? It's because when you use the clip-based features for a lot of tasks where word order and relationship between the concepts matter, it's actually pretty terrible. Like it can't tell one word order versus another. But models like Kappa perform really well on their like benchmarks like ARO and SugarCrap, which test for these things. And it's much better at those kind of tasks. Also, if you want to do fine-grained classification, like where you like have to describe an object with many attributes, like again the shirt example with like black shirt, white collar, green buttons, blah blah blah, that kind of like setting is much better handled by a generative model trained with the generative loss than contrastive loss. And they showed that it has very good performance on tasks like OCR as well. Okay, so now let's take a second to think about those tasks that we had talked about in the beginning. This image is from the Flamingo paper from 2022. And why I'm bringing it up is because here you can see that basically all of these different kinds of tasks. So in the first one, there's like a captioning kind of task. There's like an image, it says this is a chinchilla, blah, blah, blah. And then you have like, you know, like more examples of this. And then you know that you need to do captioning. Whereas in the third one, there's an OCR task because there's an image and then the, you know, what's in the image, that's clearly the task. And you can tell that by looking at the example. So this is what you call like few shot. And at this point, all the tasks basically began to be converted into a language modeling format. So, you know, you show the model what you want to do, either like by explaining what you want to do or showing a few examples. And then the output is always just like, you know, a textual description of like solving that task. And this is actually super powerful because you can even do things like object detection, which so far, you know, people had like very complicated architectures and like training strategies for doing this. But there's this paper called Pix to Seek, and then like follow-ups like PaliX, where you can just give the prompt as like detect blah, 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 like knife and left half of watermelon. So like you're really, you know, in full open vocabulary regime here. It's not no longer like shoes, cat, dog, which was like what Coco was. And yet your language model can like predict the bounding boxes in a way which is like super clean. And so this was super powerful. At this point, all the tasks that they can be solved in one unified format. And it was also the beginning of multimodal chat, which, you know, is how we all interact. Like if you use Gemini, ChatGPT, whatever, like the fact that you can say, give an image, ask some questions, and then follow up with more questions, etc. So far, it was not a thing. Flamingo is basically the paper which made this possible by training on interleaved image text data. So what that means is like you can see in the bottom here, there's an image, and then it says this is a very cute dog, cat, this is, etc. And so if you train on a lot of interleaved image text data sets like this, basically you kind of enable the few shotability capability of like the model. So yeah, this was kind of important. Yeah, just more examples to show how that worked. Okay, so if you have any questions, you can ask me now or in the end. But basically this last part is about modern VLMs. Yes, question, I'll start.
So just a short question about this tokenize everything approach. So you
Yes.
showed the output that just gives you 4 coordinates, right?
Mm-hmm.
So are we basically guaranteed with the models that it will output you these 4 coordinates every time? Or can it actually give you something very noisy that you cannot really parse and use? How do you handle this?
For sure. So I think like as language models have improved, they are better at following instructions, and we'll talk about that also with like post-training, for example. So generally what happens is for the pre-trained models where they don't really understand what you're asking them, they're just like learning from large corpus. It does happen a lot that the model doesn't follow like the pattern that you're expecting. Also like sometimes maybe it'll predict it in like JSON format instead of like, you know, whatever you want. And so the way to like sort of deal with that is by giving multiple shots. That is kind of a way that works pretty well, where you show like input output examples, and then if it's like a large enough language model, it usually learns to like give the response in the correct order. And then if you're interested in doing it 0 shot, like just give me a bounding box of X, then for sure you need like some amount of post training to be able to like, yeah, handle that. Anyone else? Okay, so let's talk about modern VLMs then. So what are the main components of modern VLMs? One, you have, of course, a large language model. The large is double here, sorry, large LLM. And then the second is a vision encoder. And the third is a module that somehow like adapts the LLM to understand the visual inputs, either right from the beginning or after the fact. And we'll see examples of both. So first way of adapting the LLM is you first train the language model just on text. So this is a example, or sorry, the screenshot from the Llama 3 paper. They show the language model here, and you'll see that there's like every fourth layer, there's like a image representation connection. So they first train the language model, freeze the language model, and have cross attention to the visual features. So there's pros and cons of doing this. The pros are that it's actually easier to train because you won't be destroying your like language model with some like possibly noisy data. Often we train large language models, the vision language models, on like all text data from the web, like Lion, etc., which are not super clean. And this way you're kind of protecting your original language model from being like destroyed, the weights from being destroyed with that. The cons are there's of course limited cross-modal interaction because you're just kind of post hoc adapting it, which is very different from the model learning about like images right from the beginning. And so that second approach is what's used in models like Pixtral, which is the one on the bottom right, and Blip2. At this point, you can also decide, like, do you want to give all the features? Like we talked about, having early fusion by giving just the image, or all the patches of the image after a vision transformer. Or in the case of Blip, basically they use something called a querying transformer. This idea is also used in Flamingo. It's called perceiver resampler there, where the idea is basically after the image encoder, you have all of the features, but then you pass it through a separate transformer with a fixed number of input queries, often randomly initialized, and then it learns how to specialize those queries for the task of interest. So this is a different way of adapting as well. So yeah, just to show you how it works in Gemma, which is something that I worked on, you have an image, and then you have this like text-based prompt, and then the vision encoder here gives you 4096 tokens because it processes images at quite a high resolution of 896. The text tokenizer gives you the text tokens, and then you have a 2D reshape of this output of the patches that come out from the SIGLIP model. Those are then average pooled to give you 256 tokens. So at this point, you're going to say, why do you do this? And so we have to think about how these models are trained. If you have a fixed training horizon, you're basically going to have like n number of, or like n trillion tokens that you're going to train with, for example. Then it will decide basically how many images you'll see depending on how many tokens you represent each image by. So ideally, of course, you would provide all the patches at the output of the encoder, but in practice, it's quite expensive to do that. And yeah, it's a trade-off that you basically have to make. And this is what it looks like. It's just, if you remember from all of the slides before, this is the full self-attention, intermediate fusion kind of approach where you still have an encoder, so it's not early fusion, but it's not, it has like self-attention on the concatenation of on both of the modalities. Just trying to connect back to what we already saw. Okay, so just the last part about like the different kinds of training phases. So pre-training and post-training are like how we kind of divide large vision and language, or even language model pre-training into. I want you to think about pre-training as basically compressing the whole world's information into the model's weights. You train on massive amounts of data with just like a next token prediction loss. And this like causes the model to basically like compress all kinds of facts, all kinds of information from like, if you're training on Wikipedia or like whatever, into its weights. And then post-training actually shapes the behavior or the personality of your model. So in the case of like detection, like someone asked earlier, like how do you make sure that it even gives you these 4 coordinates one after the other? You're going to teach it that during post-training. So we'll see how like that works, but that's basically what makes the model more robust. And then, you train also on more like targeted data. You kind of explain formatting to the model, like this is what JSON format looks like, this is what Markdown format looks like, so that whatever way the user finally ends up using this model, it's going to like work well. So it basically turns this like next token predictor into like what is an actual product that people can use in their day-to-day lives. So what are the important things to think about for pre-training? So web scale data is generally very noisy. So step one is quality filtering and safety filtering. So you don't want anything, your model to learn about questionable things from the internet. So you filter that. Quality is like basically, there's a lot of things where if you scrape the internet, like the image will have associated text, which is completely not about it. Like, oh yeah, captured, on a iPhone 16, blah, blah, blah. Like that's not going to tell you that it's an image of a boat, like, sailing or whatever. So you want to start filtering for those, make sure that you can run some like similarity metrics between the image and text tokens, and then see if like they're actually talking about the same thing, and then decide if you want to keep that data. And then the next is deduping. This is really important because training is expensive and you don't want to be training on the same thing many, many times. Repetition really is a problem in large-scale data sets because, of course, the same thing is mentioned many, many times in many different ways, and sometimes it's quite redundant, so you want to dedupe. Also, of course, you want to dedupe against all eval sets because otherwise your benchmarks are not going to tell you any amount of progress that you're making. And then the third is to adjust your data distribution to cover all the domains. So like in the vision and language case, you want to think about like, okay, I want to be good at answering questions on charts. I want to be good at OCR, medical data, like whatever it is. Make sure that during pre-training, it sees a bit of everything so that you're like well-placed when you want to use this model for a variety of tasks. And yeah, just want to point out that even like small quantities of very high quality data make a huge difference. And so like, if you embark on this journey, make sure you pay attention to your data. And extract as much juice from pre-training data as possible. So like Llama 3 also in the paper, they mentioned like that they, for example, run an OCR model on their images so that they can get additional like annotation from it. And yeah, so basically like try to reformulate your data in as many ways as possible so you can like learn as much as you can from it. Yes. Yeah, so that's where like the retrieval-based metrics of like late fusion come up. Basically, that's the kind of the way to do it. You build like embeddings of different data sets, and then you compare it based on that, like some sort of semantic similarity search. So some important considerations, especially because the things I said before are pretty much for all language, but specifically for vision, it's important to like know before the fact whether you want to have a model that's specialized to just do vision or actually keep its general usability as a general purpose vision and language model. The example I'd like to point out here is like, for example, PaliGemma. This was a model also from like a collaborating team at DeepMind where they took the Gemma models and then continued fine-tuning it on vision tasks. And at the end, you have like really good, powerful object detection models, segmentation models, all of this, but it's no longer very good at like summarizing your email, for example. So yeah, it depends on what you want. Whereas on the other hand, like Gemma 3-like models aim to maintain performance on everything while also being good at vision. And this will decide how you like train it, basically. Oh no, so close. Okay. Yeah, so the type of visual encoding also decides, like I was saying earlier, how many images you'll see. Of course, the more images you see, the better your model is going to be. And this is like kind of that's why Blip2 basically tries to do this. Like query transformer tries to reduce the amount of like visual tokens that will go into your LLM, as opposed to like, for example, Pixtral, which passes all of the patches at the output of the encoder. The third thing, which is quite important, and I'd like to point out, is aspect ratio of the image. So it's actually really important to handle this carefully because, for example, tasks like OCR, where you want to take a picture of your receipt, if you have this like really long receipts that you get sometimes and you take a picture and you upload it to like whatever, some model, and if it's going to square resize it, it's actually quite hurtful because you can't read the text anymore once you like squeeze it. And so being careful about like this, handling aspect ratio well is quite important. And Pixtral, for example, adds image breaks. So like you have a whole row of images, patches from your image, and then it tells the model like break because this is where the first row ends. And so in this case, no matter what like orientation or aspect ratio you provide the image, the model will know like where that thing kind of ended. And that's a pretty smart way to like handle this. Okay, and then we talk about post-training. So post-training is used to adapt models to specific domains, tasks, or user needs. And the main point here is to like make sure it's aligning with human preferences. And how do we do this? So there's three basically like overarching ways. You can either fine-tune the full model or do some sort of like LoRa or adapters, which Ivan talked about. There's instruction tuning, which is super important because this is what makes the model actually listen to you and like say things in a particular style, say things like, you know, in the way that you want it to respond. That's kind of what makes the difference in like how robust the model is to like following instructions. And then the third is preference optimization. So here it's like, you know, do people prefer like more chatty models? Do they want it to be more concise? Like you notice that sometimes new versions of like proprietary models suddenly start like giving you lots of emojis. That sometimes because like, you know, something went kind of sus in this like preference optimization stage probably. And so yeah, so this is how you like this is what you use to kind of make the model more like in the way that people want. Okay, yeah, so just more, that's what I just said. Cool, so just some examples of cool stuff you can do, like, because it's not just captioning and like, you know, charts anymore, captioning and VQA anymore. Here it's like, I'm sure a lot of you who are PhD students are often like, ah, damn, I really need to like transcribe this like annoying long expression back into LaTeX. Give it to Gemma 3. It does a pretty good job. So yeah, things like this are really cool. And then like more like high level reasoning task, I went to Prague this year for New Year's, and like, you know, I had the ticket, so I tried seeing how good the model was at it, and it's like basically how much does this cost, and like how long is the ticket valid. It can basically look from the picture and like figure out does this like 24 sign, and like, you know, it probably means that the validity is this much, etc. And a lot of the models now are like trained massively like multilingually and multimodally, and so I think it's really powerful time to like get into this field because the kinds of things that are possible are like, yeah, I would not have imagined them to be possible so soon when I started my PhD, like, whatever, N years ago. So yeah. And this is a video. I will try to play. How do I do that? This is my last slide. It's a demo from the Gemma 3N model, which you can use if you have an Android phone. Basically, it comes like on the app. But it's a very small model, just like less than 4B parameters, and it can do really cool things. So I'm gonna hope that it plays.
Can you tell me about this replica?
Certainly. This is a replica of a Virgin Galactic Spaceship One, a suborbital spacecraft. It's a model of the vehicle used for testing and demonstration flights.
Can you please save these to my notes?
Absolutely. Creating a note.
What can I add to the system to make it faster?
Interesting question. Adding caching layers can significantly improve speed. Consider implementing a CDN or caching proxy to store frequently accessed content.
Write a super short poem that highlights her skills.
Amazing Zoe, so bright. Counting to 100, what a sight.
What is the total square footage of the largest room?
The largest room is the living room. Its dimensions are 18 feet by 12 feet. The area is 18 times 12, which is 216 square feet.
Can you guess which famous figure is this?
This is a cartoon drawing of Einstein. The wavy hair, the mustache, and the mischievous grin are all telltale signs.
Thank you.